if you were actually doing the inspection of a surface and you noticed that Y was rising much faster than it was in X, you could choose a different U. You could do that. Generally on the CAD system, when we go click, 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 what's it assuming? An even distribution, because you haven't told it anything different. So when you're clicking on a CAD system, it's assuming that U is a fixed distance between these things. So that is a spline, the definition of a spline, which interpolates every point that you give it. Okay? If we're back to creating NURBS, so if we go back to the equations on the front page, if we're doing NURBS and we don't have the button click that gives us control points, and we're just clicking along, what does the CAD system have to do? Well, it has to fill the left-hand side with how many ever points you clicked, right? It's filling the left-hand side of this equation. It's assuming a certain distribution of U. It's assuming that if you're giving it 4 points and you're saying put a curve through these 4 points, it's assuming that the first one is 0, the first point is 0. It's assuming the second point is 1/3 of the way along. It's assuming that the third point is 2/3 of the way along. It's assuming that the last point is 1 for U. So it fills up the U values. It has 4 unknown points. Does it have 4 unknown points? Back to...
Just two.
Why do you say only 2?
The endpoints are defined.
Because the P0 on the right-hand side and the P1 are known. If we go back up here. So it knows a couple of these. It knows the first one and it knows the last one. So you have too much information, right? You only have 2 unknowns and you have like 4 equations that you're working with, okay? Is that an easy problem to solve for the CAD system? Yeah, it's an easy problem to solve. If you've got more equations than you need, what do? You just lose a few of them, right? Okay, so it's an easy problem. The CAD system has to hold on to the curve in terms of what? In terms of the right-hand side, not in terms of the left-hand side. It is solving for the left-hand side and turning on little pixels on the screen to make this curve light up. Okay? So it wants to have the right-hand side done, so when you're in there clicking 4 points and the curve goes through it, and it's a NURB, it's very quickly doing the inverse problem, solving for the control points, okay? Solving for the control points so that it can get an equation that it can hang on to, and then based on when you do a redraw or repaint or you shift your orientation, the thing will be able to draw that curve and draw it very quickly. Okay? Whoops. That away. How are Hermite splines different? You should have read in your book or just glanced at the Hermite section. What is the Hermite spline defined by? How is it defined? Is it defined by points along the curve? It's not. It's defined by beginning and end point and 2 slopes. It has the slope at the beginning and the slope at the end. So it still needs kind of 4 pieces of information to define it. On NX, it's called a bridge curve. On the way you get it on CATIA, it's not referred to as a bridge curve, it's just a spline, but you specify the beginning slope and ending slope. And with that, you can blend between two surfaces, or two curves. If you have a curve here, and you have a curve over here, it's very easy to grab the beginning point, or excuse me, the end point of the curve, which is the beginning point of the new curve that you want to bridge. And you grab this curve, the beginning point of the second curve, and as you grab those things, if you say, use this curve's tangency and use this curve's tangency, you get this really nice smooth curve that blends between those two curves, and it's a Hermite spline that is being defined. CAD system will, NX refers to it as a bridge curve, which is an excellent function for connecting curves together. In CATIA, you just need to make sure that you say this tangency and this tangency, and you'll get the same effect as a bridge curve in NX. Questions on the mathematics of curves?
I guess I'm wondering, like, if you have a spline where all the points are defined by the user. In CATIA, I know you can still go back to the original tangencies, and there's like a little vector that you can adjust, but the points remain the same. So how does, I mean, using that equation we have for a spline, it doesn't account for like that original tangency. It just has the points that you put in. So how does it create the new curve as we move that vector? Does that make sense?
So it's probably not a spline. It's probably a B-spline or a nerve. And so it's taken all of these points, it has reversed it, solved the inverse problem, has this control net, and when you say, show me these things, you can actually kind of pull on it, and those original points may or may not be still interpolated.
Okay.
They may go through it, they may not. If you've actually physically put points in, and those points are smart points, then the curve will be forced to go back through it, but you're going to introduce all kinds of ripples and waves into that curve that normally would have been smoothed out from the original creation. Okay? Question?
Yeah, on that last example, you did the X mapping coefficients.
Yep.
The 3x3 matrix, how did you get that again? I know that the second row is for the distances, but the first column.
So this is the actual expansion of that polynomial, the spline polynomial. We can break it into a row vector and a column vector. You multiply them together, you get that polynomial. And so for every p that we get, we have to have this equation, okay? And so for our first x value, we have this row and that column. For the second one, we need another row of u's times this to be the second equation. For the last one, we need this row times that column. If it were 4 points that we were using, what would this middle vector be, or middle matrix become? A 4x4, because it's 1u squared u cubed. If it were a 20th, we were putting in 20 points, what would this become? Ugly. Okay. It would go up to u to the 19th, right? So it'd just be, it's a normal spline is ugly. Why is a B-spline or a NURB a much better formulation than a straight up spline? Is because we can keep the order of the curve low, and we can group together a bunch of third order, fourth order curves into a single curve. That's the beauty of the B-spline or the NURB, is it basically links together lower order curves into a single curve, a single NURB or B-spline.
Does it do that just because, you know, further points will have such a minute effect on that early portion of the
Yes.
curve?
And so there is a the book talks briefly about non-vectors. And non-vectors basically are a weighting as to how much influence these later segments have on this earlier segment. Other questions? You already throw that up? Oh, it's right there. So we need to look at now the mathematics of surfaces. The kind of as we did with curves, we started with a basic understanding of a line. The simplest curve, the simplest surface is a surface of a plane. Its canonical form is just ax plus by plus cz plus d equals 0. In terms of points and a normal, we can usually represent it as p0 minus p1 dotted with the normal. And so the representation in this illustration is that if we have some vector that lies in the plane, the vector is from p0 to p1. If we have that vector and we dot it with the normal, then it defines a plane. Well, in terms of how do we get from this point definition to back to our XYZ definition, well, we choose one of these points as a variable, the variable XYZ. And it just so happens that if we choose this P1 as our value XYZ, we have to then know a real XYZ that's in the plane, and that's the point P0. And so this vector could sweep any place in that plane, or all vectors in the plane, because X, Y, and Z are changing based on that equation, okay? So we're just saying that if the angle between these things is equal to 0, okay, then we can define a plane. And so what gives us the A, B, C, D coefficients? Well, it's the normal times the P0 collected together, and all of that becomes kind of the coefficients and the distance from the origin. So let's assume that we have some box. How can we represent that with equations? Well, it's pretty simple. We just say, if it's a regular box and it's oriented to the XYZ, we just say x of 0, x of 10, y of 0, y of 15, z of 0, z of 10, and those 6 planes or 6 equations define for us a simple box. The quadratic, so that's kind of the linear representation. The quadratic representation gets somewhat ugly. You may remember this from your calculus or algebra days. This is the canonical form of a second degree second degree surface. Okay. We, however, know some simplified versions of that. For example, what is the equation of a sphere? Well, it's just x squared plus y squared plus z squared equals r squared. What's a more general equation for that? This sphere is always located where? At the origin. Okay. If we don't want it at the origin, how do we get it someplace else?